Hi friends, this is Naresh. This is my sixth lecture on mechanics of solids or strength of materials subject. This is common for B.Tech second year and diploma second year mechanical students. Uh, in this session, I am going to explain about simple problems on simple stresses and simple strains. Okay, in this session, I will discuss about 5 problems on stresses and strains. These problems are basic problems for mechanics of solids subject. First problem is a steel rod 1 meter long and 20 mm by 20 mm in cross section is subjected to a tensile force of 40 kilonewtons. Determine the elongation of the rod if modulus of elasticity for the rod material is 200 gigapascal. Okay, this is the question. Here, the original length of the rod is given, that is 1 meter. Okay, length of the rod equal 1 meter, that is 1 into 10 power 3 mm. So 1000 mm. Okay, 1 meter equal 1000 mm. This is the original length. Okay, and the cross section of the bar also given, that is a 20 mm by 20 mm, that is a square cross section. 20 by 20 mm, that is a square cross section. Okay, this is a cross section. Okay, this is a length. Okay, this is the original length. This is the length of a bar. Okay, this is length L equal to 1 meter. Okay, 1 meter or 1000 mm, and this is a width equal 20 mm and height also 20 mm. Okay, these are the dimensions for rectangular or square bar. Okay, and the load acting on this bar also given, that is 40 kilonewtons, that is P tensile force is given, that is P equal to 40 kilonewtons. Okay, here 1 kilonewton equal to 1000 newtons, so 40 into 10 power 3 newtons. Okay, this is the total load acting on the bar. And the modulus of elasticity or Young's modulus. Young's modulus or modulus of elasticity, capital E equal to 200 gigapascal. G, capital G means gigapascal. This is a G. Okay, so 200 gigapascal. 1 giga equal to 10 power 9 pascal, and here 1 giga equal 10 power 9 pascal or 10 power 3 Newton per mm square. Okay, so these are in mm. So here cross section is given, length, the original length is also given, and the load acting on the bar also given. Thus P and area and length and Young's modulus. Okay, so these 4 values are given in our question. By using these four dimensions, we have to find the value of elongation or change in length or extension. Okay, so you have to find the value of extension or elongation or change in length, that is you have to find the value of delta L. Okay, already we know the formula for Young's modulus, capital E equal to stress by strain. Okay, and also Young's modulus, capital E equal to stress equal to load by area divided by strain equal to delta L by L. Delta L is the change in length by original length. Okay, here there is no units for strain, and the units for stress equal to Newton per mm square. So Young's modulus also in Newton per mm square. Here the value of P is given capital E also we know, and original length also we know that. First of all, you have to find out the area, cross-sectional area of this rod. Okay, this is a square rod, so therefore cross-sectional area equal to 20 by 20. Okay, capital A equal to 20 by 20. Okay, that is 20 by 20 equal to 400 square. Okay, this is the area. So here only we don't know the value of delta L, that is change in length or elongation or extension. So the formula for change in length or elongation delta L equal to uh, P into L by area into Young's modulus. Okay, this is the formula for change in length. So then we have to substitute all these values in this equation. Then after you will get the answer, that is a change in length or elongation, that is equal to 0.5 This is the answer for this problem. Okay, this is a simple problem on stress and strain. Okay, and coming to the second problem, that is this problem is on hollow pipe. Okay, so first of all, the given problem is a hollow cylinder 2 meters long. So this is the original length. So this is the original length of the cylinder, that is L, capital L, and has an outer diameter. Outer diameter means capital D equal to 50 and inside diameter means small d, inside diameter equal to small d, and inside diameter 30 and outside diameter 50 Okay, capital D equal to 50 small d equal to 30 If the cylinder is carrying a load of 25 kilonewton, that is a load P. Okay, this is P. Here this value is P. The stress inside it, find the stress, that is you have to find the value of sigma. Okay, you have to find the value of sigma. So here find the deformation and also find the deformation. Deformation means change in length and or change in diameter. Okay, if the value of modulus of elasticity for the cylinder material is 100 GPa, that is capital E, Young's modulus or modulus of elasticity equal to capital E. Capital E equal to 100 GPa is also given. So these are the given values. So here given actual length L equal to 2 meters. Okay, 1 meter equal to 1000. 1 meter equal to 1000 So 2000 and the outer diameter here, this is the shape of a cylinder, hollow cylinder means it has a internal hole. Okay, so this is the cross section of the pipe. So this is the internal inside diameter and inner diameter, this is the outer diameter. Okay, so capital D equal to 50 and small d equal to 30 Okay, these are the dimensions for this pipe, and the load acting on this pipe is P equal to 25 kilonewton. So you have to convert this kilonewton into newtons. So 1 kilonewton equal to 1000. So 25,000 newtons. And the modulus of elasticity equal to 100 GPa. 1 GPa equal to 10 power 9 Newton per meter square or 10 power 3 Newton per square. Okay. So this is the value of Young's modulus. These five are the given values. By using these five values, you have to find the value of change in length delta L and stress. Okay, you have to find the value of sigma and delta L. So the formula for cross-sectional area of a hollow cylinder equal to pi by 4 d square minus d square. This is the formula for area. Okay, the cross-sectional area of this hollow pipe equal to 1257 square. Here the capital D and small d both are in mms, so the area also in mms. Okay. Then after the formula for stress equal to load by area. So load 25,000 is given and area equal to 1257. the area of the hollow cylinder. Already we have found that. Okay, so the final answer for stress induced in the cylinder equal to 19.9 Newton per mm square. Okay, here 1 Newton per mm square equal 1 megapascal. Okay, this is the answer for stress induced in the hollow cylinder. And then after you have to find the value of change in length, that is delta L. For finding out the value of delta L, you have to know the value of stress strain. Okay, so Young's modulus for already we know the formula for Young's modulus, that is capital E equals stress by strain. Already we found that stress equal to 19.9. Okay, the formula for Young's modulus equal to load by area by change in length by origin length. Here change in length or delta L is the change in length or elongation in the pipe. Okay, so here the value of P by A equal to 19.9, and delta L we have to find the value of delta L, and the original length L is also given, that is 2000 meters, and the capital E also we know that. So substitute all these values. Okay, here you have to find the value of deformation in length, that is delta L. So the formula for delta L equal to P into L by AE. Okay, substitute all these values in this equation, you will get the answer. Okay, the change in length or deformation in the cylinder or extension in the cylinder, delta L equal to 0.4 mm. This is the answer for this second problem. Okay, now coming to the third problem, that is a problem on wire, simple, a small diameter wire. Okay, this problem is on circular cross section. Okay, here the given data is load. A load of 5 kilonewtons is to be raised with the help of a steel wire. Find the minimum diameter of the steel wire if the stress is not to exceed 100 megapascal. Okay, this is the question. In this question, the load acting on the wire is given, that is P. This is the value of P. Okay, this is P. Here find the minimum diameter of the steel, that is you have to find the diameter of the wire, that is capital D or small d. Here the stress is not to exceed 100 megapascal, that means stress is given, this value is stress. So sigma and diameter and load acting on the wire, these three values are given. By using these three values you have to find the sorry, here only two values, only load and stress. Okay, these two values are known. Okay, you have to find the value of diameter of the wire. Okay, here this is the shape of a wire and this is the cross section of the wire. Okay, here the diameter, only one diameter is given. Okay, so that is solid. Okay, wires are always in solid shape, so you have to consider a solid circular cross section. Okay, capital D is the diameter of the wire. So from given data, load P equal to 5 kilonewtons. 1 kilonewton equal to 1000 newtons. So 5000 newtons, and stress equal to 1000 megapascal. 1 megapascal equal 1 Newton per mm square or 10 power 6 Newton per meter square. Okay, and here small d or capital D equal to diameter of the wire. Okay, already we know the formula for stress equal to load by area. Okay, here the load acting on the wire is given, so P equal to 5000 newtons. Here the capital A is the area, cross-sectional area of this circular cross-section. So the area of the cross-section is pi by 4 d square. Okay, pi by 4 d square is the area of a circular cross-section. So you have to substitute the values of load and area. Okay, here the value of stress equal to 100. So you have to substitute the value of stress equal to 100 Newton per meter square, and P equal to 5000 newtons by area equal to pi by 4 d square. Here small d, you have to find the value of d. Okay, so here from this equation we got the answer. Diameter small d equal to 7.98 mm. The rounded value of d equal to 8 mm. Okay, this is our required final answer for this problem. Here d is the our required diameter of the wire. Okay, so this is a complete answer for this third problem. Okay, here only one formula, I used one formula, that is stress equal load by area. Okay, so from this formula I got this answer. Okay, we're coming to another problem, that is problem number 4. Here the given problem is in an experiment, a steel specimen of 13 diameter was found to elongate 0.2 in a 200 gauge length. Okay, when it was subjected to a tensile force of 26.8 kilonewtons. If the specimen was tested within the elastic range, what is the value of Young's modulus for the steel specimen? Okay, so this is the question. Here by using this data you have to find the our values. Here a steel specimen, that is a 13 diameter, that is a d. Okay, here diameter d is given, that is d equal 13 was found to elongate means elongation or change in length, that is a delta L. Okay, this is a delta L equal to 0.2 Okay, and this is a 200 gauge length. Gauge length means original length, that is L. Okay, this is original length L. This is change in length delta L. Okay, when it was subjected to a tensile force, that is tensile force means load. Here the units are in Newton, that means load. Okay, this is P. Okay, this is a P. If the specimen was tested within the elastic range, okay, what is the value of Young's modulus? Here you have to find the value of Young's modulus. Young's modulus of the steel specimen. Here Young's modulus or modulus of elasticity, capital E. You have to find the value of capital E. Okay, here the given values are here. This is the shape of a specimen. This is also in a cylindrical shape. That is here the values are in diameter. So diameter means a circular cross section. That's why I consider a circular rod, and the cross section of this rod equal to capital D equal to 13 Okay, outside diameter equal to 13 is also given. Okay, and the length of this rod equal to 200 Okay, the original length of the rod equal to 200 After elongation, after loading, the elongation delta L equal to 0.2 and the load acting on this rod equal to P equal to 26.8 kilonewtons. Okay, by using these values, you have to find the value of Young's modulus for this specimen. Okay, here these are the given values. Okay, diameter d equal to 13 and elongation delta L equal to 0.2. Elongation means change in length. Okay, and length, original length equal gauge length or original length equal 200 Load acting on the bar equal to 26.8 kilonewtons. Here Young's modulus of the specimen capital E, you have to find the value of capital E. Okay. Now, first of all, you have to find the value of area, cross-sectional area of the specimen. So the cross-sectional area for a circular cross-section equal to capital A equal to pi by 4 d square. Here pi by 4 into d equal to 13 square. Okay, d is the diameter of the specimen. that is 13 mm is given in our problem. So the area of this cross section equal to 132.73 mm square. Okay, this is the area of the bar. Then after you have to use our Young's modulus formula, that is capital E. Young's modulus capital E equal to stress by strain. The formula for stress equal to load by area, and the formula for strain equal to change in length by original length. By using these values, you have to find the value of capital E. So substitute the value of load P and area. Okay. So here 26.8 is the load acting on the bar, and L is the original length, that is 20. Here divided by capital A equal to 132.73, and change in length equal to 0.2. Okay. And the final answer for this problem, Young's modulus of the specimen equal to 201.9 kilonewton per mm square. Okay, so this is the answer for this problem. Okay, yeah. Now coming to the last problem in this session. So this is a different problem. Okay, here the question is two wires, one of steel and other of copper. Okay, other of copper are of the same length and are subjected to same tension. If the diameter of the copper wire is 2 mm, find the diameter of the steel wire if they are elongated by the same amount. Take Young's modulus for steel as 200 GPa and that for copper as 100 GPa. Okay, this is the question. Here the given data is here two metals are given, that is one is steel, another one is copper metal. So here steel rod and copper rod are given. Okay, yeah, these both steel and copper rods having same length. Okay, that is the length of a steel wire equal to length of a copper wire. Okay, and here subjected to same tension. That means the load acting on both the rods are also same. Okay, and the diameter of the copper wire is given. The diameter of the copper wire is equal to 2 mm is given. Now we don't know the diameter of the steel wire. You have to find the diameter of the steel wire. Okay, in this question you have to find the diameter of the steel wire. When steel and copper wires are having same length and the same load, then you have to find the area, then you have to find the diameter of the steel wire. Okay, here the if they are elongated by the same amount, that means change in steel wire equal to change in length in steel wire equal to change in length in copper wire. Elongated by same amount, that means change in length in steel wire equal to change in length in copper wire, both are same. Okay, this sentence meaning is change in length. Change in length in both the steel and copper wires are same. Here the Young's modulus for steel, Young's modulus for steel equal to 100 GPa, and also Young's modulus for copper equal to 100 GPa. Okay, here the Young's modulus are different for different materials. So here the steel metal is different and copper metal is different. So Young's modulus both are also different. Okay. Here the steel metals have having high strength. That's why the Young's modulus of the steel is higher than the Young's modulus of the copper. Okay. So this is the given data. Here modulus, Young's modulus or modulus of elasticity. Young's modulus or modulus of elasticity of the steel material. Capital E here, capital E is the Young's modulus, and suffix S refers steel. Okay, suffix C refers copper. Okay, so Young's modulus for steel material equal to 200 GPa. Okay, 200 GPa. Then after you have to convert this gigapascal, where G is the gigapascal. You have to convert this gigapascal into megapascal. Okay, so here 1 gigapascal equal to 10 power 9 Newton per meter square, or 10 power 3 Newton per mm square. So here in mms, 1 gigapascal equal to 10 power 3 Newton per mm square. Okay. Similarly, Young's modulus for copper material equal to 100 gigapascal. So 100 into 10 power 3 Newton per mm square. Okay. And here the diameter of the copper wire is given. That is the diameter of the copper wire, D suffix C. D is the diameter, C is the copper. Okay. So here diameter of the copper wire, D suffix C equal to 2 mm. Okay. Then you have to find the diameter of the steel wire. So D suffix S refers to diameter of steel. Okay, D is the diameter, S is the steel wire. Okay, diameter of the steel wire equal to ds. Okay, here the length of the steel wire and the length of the copper wire both are same. Lengths of both the wires are same, and also tension here, same tension is induced in the both the steel and copper wire. That means load acting on steel wire equal to load acting on copper wire. Okay, this means load acting on steel wire equal to load acting on copper wire. That is equal to P. Okay, this is the question. So by using these details, you have to find the unknown diameter of the steel wire. Okay, here this is one material. Okay, so this is a copper. Okay, this is a copper material, and another one is steel material. Here these both copper and steel, these both are having, these both are having same length. Okay, that is L, original length is L, this original length also L, capital L, both are same length, but these two are different materials. That's why the Young's modulus of copper is different. Okay, and this is the Young's modulus of the steel. Okay, so here steel material having high strength, that's why the Young's modulus of the steel wire is higher than the value of copper. Okay, so that's why there is a difference between strength. Okay, then the diameter of the copper wire and the diameter of the steel wire both are different. So that's why you have to find the diameter of the steel wire. Okay, here this the diameter of this copper wire equal to 2 mm. Okay, then if load acting on this copper wire and this steel wire both are same, then find the diameter of the steel wire. Okay, so here the strength of the steel wire is higher than the strength of the copper. That's why the answer for steel wire, that is the diameter of the steel wire, has a smaller diameter. Okay, smaller diameter than the copper. Okay, here Young's modulus, if the here the relation between Young's modulus and cross-sectional area is in inversely proportionality. Okay, that's why if the Young's modulus of the material is high, then the diameter of the material is low. Okay, so by using that relation, you have to find the suitable diameter of the steel wire. Okay, so first of all, you have to find out the cross-sectional areas of steel and copper wires. Here the diameter of the copper wire already is given in our problem. That's why the area of the copper is equal to 3.142. Here both are in circular cross sections. Therefore, pi by 4 d square is the area. Okay, dc is the diameter of the copper. The diameter of the copper wire equal to 2 mm. So the area of the copper equal to 3.142 mm square. Here the diameter is in mm, so the area of the copper also in mm square. Then the diameter of the steel wire, we don't know the value of diameter of steel wire, so that's why the area of the steel wire is in terms of d, in terms of diameters. Okay, here ds you have to find the value of ds. Okay, so then after one relation is given, that is Young's modulus. Young's modulus equal to load by area divided by change in length by original length. That is a stress by strain. Okay, Young's modulus equal to stress by strain. Here another relation is given, that is the change in length in copper wire is equal to change in length in steel wire. Okay, so from that relation you have to use change in length formula. Okay, from this relation the formula for elongation or change in length, delta L equal to load into length. Okay, load into length divided by area into area into Young's modulus. By using this formula you have to find the suitable diameter of the steel wire. Okay, so the extension in copper wire. Okay, the or change in length in copper wire equal to load into L by area of the copper wire into Young's modulus of the copper wire equal to, here the load acting on the copper and steel wire both are same and length also both are same, but these two values are not given, so the equation also in load and length. Okay, so yeah, this is the answer for change in length in copper wire. Similarly, the change in length or increase in length in steel wire equal to delta L S. Here suffix C refers copper, suffix S refers steel. Okay, so here the change in length for steel wire equal to load into length. Load acting on steel wire, length of the steel wire divided by cross-sectional area of the steel wire into Young's modulus of the steel wire. Okay, substitute all these values. Then after you will get the equation. Okay, here also load and length both are unknowns, and hence here area of the steel wire is in the diameter of the steel. So here ds also unknown value. Okay, here in our question the change in length in both the steel wire and copper wire both are same, so that condition is given. So from that condition you have to equate equation 1 and equation 2. Okay, so from the question equating equations 1 and 2. Okay, here the PL in left side, a PL in right side, both are same, so both are cancelled. Then there is only one unknown in the equation, that is the ds square. Okay, then the diameter ds, diameter of the steel wire ds equal to square root of 2. Then the answer for steel wire equal to 1.41 mm. This is our required diameter of the steel wire. Okay, here the diameter of the copper wire equal to 2 mm. Okay, so the Young's modulus for copper equal to 100 mm, 100 GPa, but the Young's modulus for steel wire equal to 200 GPa. So that's why the diameter of the steel wire is less than the diameter of the copper. Okay, so this is our required size of the wire. Okay, okay, in this session only I used two formulas, that is Young's modulus equal to, here I used a formula of Young's modulus. Okay, this is the main formula in our session. Okay, Young's model is equal to stress by strain. Okay, now the formula for stress equal to load by area. Okay, and the formula for strain equal to change in length by original length. Okay, change in length also known as extension or compression or change in length. Okay, so delta L by L is the original length, delta L is the change in length. Okay, so this is the only one formula I used in this session. Okay, this is the main important formula in the mechanics of solid subject. Okay, so please all of you remember this formula for our subject. Okay, okay friends, thank you. In tomorrow class I will explain about some problems on bars of varying cross sections. That means different cross sectional areas in one problem. I will discuss in next class. Okay.